Right, so I'm going to talk about function-reactive Rust, and that means function-reactive programming in the Rust programming language. I'm not sure how many of you have been at the previous talk, but I saw there's already lots of talk going on about function-reactive programming. So I kind of hope that this context is already there. The Rust programming language maybe not so much because it's got kind of, well, it's not a functional programming language, and it's also kind of a new thing that's gaining a bit of popularity now, though. Okay, so there's two kind of angles that you can come to this topic, I guess. The first one, which I kind of come from, is you're doing some kind of systems programming. In my case, that was game development. And you have a lot of trouble with event handling, because the way you do it in imperative languages and object-oriented languages, usually this model view controller pattern, that has a lot of issues that can get troublesome in larger applications. And so I looked into FRP as an alternative and found that it solved quite a lot of these problems that I found. There's also another angle that you can get to this, I guess, which is pretty much you're already sold on FRP because you have a functional programming background or whatever. But now you get to an application domain where you maybe can't use all the nice things like Haskell or Clojure or Elixir or Elm or whatever you want to use. And so, yeah, you look for other alternatives. And I think Rust is an interesting alternative. So what I've done is pretty much write a library in Rust, in safe Rust, that I'm going to explain later what that means. And it was originally built for game development, but it's fairly generic implementation of FRP. You can get it on GitHub under my username, and also on Crates.io, which is Rust's package repository. It's a 0-point-something thing, so it's not like production ready yet, but I'm just going to talk a little bit about what it looks like at the moment. First of all, I would like to say a few words about Rust, because I would assume that it's not familiar to everybody here. So Rust basically is a systems programming language that has very much a focus on performance, and it's near C. I say near because it does quite a few things at runtime for safety reasons, such as array bounds checks. So it's not entirely the same that you can get if you write C or raw assembler or something, but it's pretty close. And the nice thing about Rust, as compared with a language like C, though, is that it statically prevents all these kind of memory corruption issues that you get when doing programming in these languages. And it does this using a static type system to figure out at compile time whether what you're doing with all your memory allocated resources is actually valid and doesn't lead to these kinds of violations. It also, on top of this mechanism, guarantees thread safety. So it pretty much follows the single writer principle, so you can never have two writing handles to the same resource. And given all these these constraints, it focuses on building abstractions that are zero cost. So pretty much everything that the compiler can just annihilate when building your application, so that at runtime you're doing pretty much the same thing that you would have done with a C program, but you have done all these checks before that it's actually safe to do so. And it also has quite a lot of functional programming features, like it has first-class functions, it uses a lot of generics and algebraic data types, which are really nice to build functional semantics with it. Now let's look a little bit about Rust code. This is the obligatory hello world program. Nothing too fancy here, I guess. It's just a main function that prints hello world. This is what let bindings look like in Rust. Yeah, you just have this. First of all, everything is immutable by default, which is a pretty nice property to work with. And you declare that you can annotate the type, but it also has type inference, so you don't need to if it can be inferred from the context. You can also, it's not a function programming language, so you can just declare a variable as mutable and assign another value to it, but you have to explicitly say so. And there's some limitations on when you make something mutable, it will not be usable in certain contexts to guarantee the properties that I talked about before. then there's the concept of ownership. So this is pretty much what a function looks like. So the upper 4 lines, there you have a vector, and you pretty much just want to look at, so it's a vector of integers, 32-bit integers. And on systems programming, you're pretty much very precise about what kind of type you have there. And if you want to calculate the sum of that vector, we can convert that into an iterator and fold over it. So we have kind of this nice functional API with a little bit of conversion between a vector and an iterator there. But the interesting part here is that when I pass the vector, like initialize some vector with 1, 2, 3 in it and pass that to the function, it will compute the result, but afterwards I can't use that anymore. So if I wanted to do anything else with the vector, I couldn't because I've consumed the vector and it's gone. So that's kind of inconvenient, but this is how Rust makes sure that you don't share certain things. Now, of course, you can't really work with something that just works like that. So you have to sort of introduce a way of sharing things. And this is called borrowing in Rust. So you pretty much can just, instead of giving ownership of the vector to the function, you can just borrow it by giving it a slice of the vector, in this case. And then you use this funny ampersand symbol to indicate, okay, I have a reference to this thing. And then you can use the vector afterwards, because after the function is done computing the sum, it sort of returns or gives the ownership or releases ownership of that value. So the surrounding scope has ownership of it again. So, right. There are also mutable borrows. So these are borrows into resources where you can actually mutate the contents. So this is how you just define some variable, and then in a scope that I note by these curly braces, you can take a mutable borrow and modify that. And you can also think doing this in a function too. But this thing, so for a given resource, you can only ever have one mutable borrow. You can't create multiple of them, and otherwise the compiler will yell at you. This is to ensure the single writer principle. Okay, just a bit more. Of course, we have structs and enums. Enums were pretty much like algebraic data types, and structs are the same thing as in C. So these are the fundamental building blocks, how you do build more complicated types in Rust. And they have very efficient representation on the machine in the end. Okay, that's so far about Rust. So let's continue a little bit about functional reactive programming. I've noticed that a lot has been talked about that at this conference already. But I'm just going to wrap up the basic idea. So you have essentially this functional approach to event handling and how this affects your application state. And you want to build these time-varying data structures like signals and streams or observables, or however you want to call them. And then you have these high-level operators on them. And this way you sort of have an immutable way of talking about application state and events that you can manipulate with purely functional functions. Yeah. Right. That said, FRP comes in a million different flavors. A million is probably a bit too much, but there are a lot of varieties. This is why I sort of want to talk a little bit what Carboxyl, so my library's flavor in particular, is of functional reactive programming. So in contrast to what many popular FRP libraries do at the moment, Carboxyl distinguishes two different types. So the first type is a stream, and this is just a sequence of discrete events. So this does not contain any state whatsoever. It just says essentially, okay, at 5 o'clock, A happened, and at 7 o'clock, B happened, and then at 7:30, C happened, and so forth. So it doesn't really persist the state of these events as its current value. For that, you have a signal, and that is a value that varies continuously over time. So it might be just an event stream held, essentially. So you just persist the state of a given event stream and just take the last one. So you have a stepwise function. So from 5 to 7 o'clock, I'm A, and from 7 to 7:30, I'm B, and after that, I'm C. But it could also be something that really changes continuously, like a sine wave or some cubic interpolation between two values if you want to do animation or computer graphics. And I find this notion of continuous time pretty useful, especially if you do things. Well, I've been doing video game development, so they were quite useful just to model these things that just sort of continuously change from one thing to another, or where you know the exact shape of the time dependency of the value. That being said, time in Carboxyl is also implicit rather than explicit, which means that you don't really write down these functions as functions of time, but you just evaluate something at a certain point, and then it will be the value that is the current value of it. So if you want, you can of course use some library to bring in explicit time, but the implementation doesn't really deal with that. Okay, so let me just give you a quick overview over all the features. This is what it looks like to just build streams and signals. So because we're in an imperative language, we sort of have to somehow tie the concept of a stream or a signal to the surrounding context and all these imperative calls. And to do that, first of all, you have something called a sink, which is basically just a place to dump events into. So you can have some kind of driver that reads from a network resource, or something that fetches keyboard events from your windowing library. And then you can create a stream from that pretty much has the definition, okay, I contain all the events that somebody at some point dumps into the sink. And with this, you can pretty much work and just do all the functional transformations. A signal then, you can, for instance, create from a stream by holding the stream and giving it some initial value, and then it will change from that initial value whenever an event occurs. You can also create, I haven't shown this here yet, signal from just a function that you might take, have some side effects, or read some input resource. So in the lower part of this code, you can sort of see what happens if I just sample the signal, which just means get its current value in an imperative way. Then it's going to be 3, and once I send something into the sink, it's going to be 5. So this is sort of imperatively inspecting what's going on there, which we don't want to do that much, but I'm just going to show the framework in which this ties into the rest of the language. Okay, you can also iterate over a stream. So Rust has mutable iterators that carry the state of, in this case, what kind of event I'm at, and then I can just call next and go to the next event if there is one. It's kind of another way to just directly consume a stream instead of sampling a signal, which might be interesting in some cases. Right, and now let's go on to the purely functional stuff. We can map, so this is a closure in Rust, so you just take a stream and a function and get another stream. In this case, the squares of whatever you put in. You can filter. There are a couple of different ways of doing that using Rust's optional type, so you can either just use a Boolean predicate and filter everything out that doesn't satisfy that predicate, or you can return an option type. So only take the sum values and not the none values. Or you can just directly operate on an option stream. So just different kinds of filtering. You can merge two streams and get a stream that contains all the events from both. You can fold over a stream and get a signal that contains, so it contains a state, it has some initial state, and whenever you send an event into it, it will call a function with current state and whatever event you get in, and should get out a new state, essentially. So this is very, very important to sort of persist application state in some way. Right, then there's Snapshot. This is pretty interesting because it takes a signal and a stream and combines these with a function. So in this example, I have a function that takes the time and some event, some value of a particular event type, and gets out some new thing, whatever that is. And so this pretty much takes, so this creates a stream, and that stream will occur every time the original stream fires. and it will sort of combine the current value of the time at the point this event has happened with using the function with the event that came in. All right. Right, another useful thing is also that you can sort of lift an ordinary function to a function on signals and then get a new signal out of that sort of just combines what you've got by using that function. This works for arity up to 4. I can't do this generically in Rust entirely because macros are not quite powerful enough, I think. At least I haven't succeeded so far. But I don't think you actually need something more than 4 because otherwise you should probably think about restructuring your function. But anyway. Right, there are a couple more things that might be interesting. For instance, I have also dynamic switching of streams and signals, which is kind of debatable because it isn't entirely referentially transparent. So this is a complex discussion. I'm kind of thinking about throwing it out actually because you might get along without it. And there's also a way to coalesce events that occur in the same transaction. So if one thing that you send in will result in 2 events that are simultaneous and are merged at a certain point, you may not want to merge them right away because then you have no control over what the sequence is. So instead you have some function that takes care of getting rid of that ambiguity. Right. So far about what it generally looks like. Now I want to talk a bit about how to actually build applications with it. And there are a lot of libraries available in the Rust ecosystem, crate ecosystem. So crate in Rust is just a library, basically. And there are a few that belong to Carboxyl directly that I sort of made into separate modules to sort of keep these concerns separate that help you interface using a streaming API for command line interface and for system time and also for windowing. So that includes like getting keyboard and mouse events from a given window and drawing to it. What's also been very helpful in that context is lmask, which is a port of AMP's graphics API to Rust. It's a very nice, purely functional 2D graphics API, and that helped a lot in just getting some basic applications set up. And then in general, there's also a lot of infrastructure around game development. There's the Piston game engine, which is pretty modular, and there are GFX and Cleum for doing 3D graphics, and there's Gluteum, which provides a pure Rust implementation of a windowing context. So there's a lot, and I'm probably mentioning half of this. I'm not mentioning half of the things that are actually worth mentioning here. The point is, though, that sometimes it's a bit hard to interface these with Carboxyl because they pretty much just use mutable state wherever they can for event handling. And that sometimes makes it a bit tricky because you sort of have to write some driver and your own declarative API to feed that into something that will then make the according side effectful calls based on your purely functional description. But in principle, there's a lot to work with. It's just a bit tricky to integrate. Yeah. So demo time is slightly problematic because we had some technical issues. So I can't actually show this right now, which is a bit annoying, but it wasn't this much of an application. So the application that I wanted to show pretty much was really just a button that you would click, and it would change its color. So effectively a toggle button. It's really nothing too fancy, and I'm still sad that I can't show it, but I wanted to talk about a little bit more how to build this anyway, so I hope you can forgive me for that. Right, so looking at the application structure, generally how you get from inputs to outputs, you have a couple of steps to take, and this is sort of the framework that wraps up how this all works. So in my case, when I'm talking about the entire application, I'm starting out with a window, which contains all these events that describe what your user does essentially. And there are two aspects several aspects that I can derive from that. First of all, we get something that I call context. it's pretty much the signal part of the input, so the continuous part. So this is like, where is the mouse currently? Or, yeah, I don't know, what is the current size of my window? These things. And in my case, I model this context just as something, okay, am I hovering my button or am I not doing that? Which pretty much describes what you want from that context. Now you have to sort of derive that from the window that you get. So yeah, there are a couple of functions that I can delegate this to, but essentially I take the window size and the current position of the mouse cursor and determine, okay, is this, make some coordinate transformation based on the window size, and then say, okay, does that hover over my button? And if so, I'm in the hovering context, otherwise I'm free of the cursor. That's pretty much it. Then there's also a discrete part to the input. The part that we are interested in this case, pretty much only clicks with, say, the left mouse button. And so we filter out everything with a function that gives the raw event that contains all possible things that could happen to an optional event that only contains one variant here. Right, now that we have these two things, we can sort of think about interpreting them. So the next step would be to think about, okay, what was the intention behind all this input that I've seen? And so I interpret the input events that come in a given context, and figure out, okay, did I want to do anything with that? Like, what did I want to achieve, or did the user want to achieve anything with that? And in this case, the implementation is pretty trivial. So we just say, okay, if I'm hovering currently and an event occurs, which in our case can only be that one click that we defined, then I want to toggle the button. Otherwise, I'm not going to do anything because a click outside the button doesn't do anything. Right. And if we look again back to the original wrapper function that put all the logic together, we'll see that how this ties together is that we take the context and snapshot it with the events and the intent function, and what we get out of it is a stream of optional actions, and we just filter the sum variants out of and take these. All right. The next thing is that given these actions, I want to have some state in my application. And there's two aspects of it. So first, I want to define what's the initial state before anything has happened, which is in this case false. I mean, I've just modeled this as a Boolean. And then there's also an update function, which pretty much tells you, okay, given the current state, when an action occurs, I want to change my state to that new state. And in our case, there's only one action that can occur, and when it occurs, we want just to negate our current state. And that's it. And this is where fold comes in, that I talked about earlier. So we just fold the action stream with these two items that pretty much satisfy the type signature of fold. Okay, and then we have a stream of states. Now we just want to transform our state stream into a view. And we also do this given a certain context, because in this case, the view depends on the context, because when I hover, I also want it to be a little bit highlighted. So I'm seeing, okay, I'm hovering, and the state. And so I just map these things accordingly. So when it's hovering, it's either light blue or light orange, and when it's not, it's either blue or orange. So where blue and orange sort of represent the color of the button. That's really sad that I couldn't show you, but okay. Right, and the way how we transform this to the stream level again is that the output, which is just a stream of views essentially, is just lifting this view function over the input signals of the context and the state signal. Right. Yeah, that's pretty much it. How you build at least one component with it. What's missing from this is, I guess, how to compose these components. And I drew a lot of inspiration from both the Elm architecture and also Cycle.js that has been mentioned in this context before, so mostly web front-end stuff. And I think it's pretty easy once you have these functions to just compose them in a certain way to new sets of functions that will act as a bigger thing. So this really composes pretty nicely. And another part that you also should think about when doing these things is how you manage effects. So effects are effectively, so we can say in some sense we already have an effect by having a signal of views, so that affects how our renderer uses OpenGL and the window context and everything to actually show us something. But there might be other things that you also want to have, like a stream of network messages sent or something like that. Right. Now, I want to talk a little bit about implementation details of the library. So my original inspiration for this was the Sodium set of libraries. So this is pretty much an implementation of FRP that is done in a variety of languages, such as Java and C#, and originally it came from Haskell, I think. And this was pretty interesting because it already started out with the separation of streams and signals, which I found pretty helpful. But later I also looked at a paper by Conal Elliott about push-pull FRP, which gave rise to this continuous notion of signals, which was good to do animations and things like that. So the idea behind that is sort of, so the discrete part of the streams pretty much pushed through the system. So I have a network of streams in a way, and when something occurs somewhere, it's just going to go forward through this network of streams and update whatever state might be affected by this event occurrence. Whereas when you have something continuous, such as the transition between a certain state given a certain interpolation function, it kind of depends how often you want to update. And that pretty much depends on how many frames per second you want. So for instance, you may want to only create a video, and then you might be fine with either 30 or 60 FPS, whatever format you use, or you're doing something with some virtual reality hardware where you need more than 20 frames per second. But you don't really want your application code to depend on that. And so it's, in this case, you would just, like at the consuming side, so when you're given a signal, you will just pull for the current state of the signal inside the system and go backwards, so to say. And that way you pretty much, like, how often you need to evaluate that function that describes the signal depends really on how much demand there is, how often you need to do that. And you don't have to worry about that in your application logic. In that particular paper, that was done in Haskell originally, and it was a very nice and elegant, purely functional implementation. I could not possibly reproduce that in Rust because there was strict evaluation, and there was also the point with resource and lifetimes, and it was just getting too complicated to do something similar to that. So looking at that, essentially, internally it uses the observer pattern, a very simple implementation of the observer pattern, and sort of automatically ties that together when you create streams and signals in the way it's supposed to be. Well, and there are some discrete changes in the system whenever an event occurs, and these have to be atomic, using some form of transactions. And the signals are already glanced over this before, are essentially impure functions. So you have some function which just gives you the system time, for instance, typical system callback in C. Or you might also measure analog instruments or whatever kind of resource you want to pull data from. And you can just create the signals from that. That is the continuous part of the signals. They also have a discrete component if you just have a stepwise thing that it was created from a stream. Right, there are a couple of problems with the current implementation. So while it's done in Rust, and I guess I pretty much had to do this without garbage collection, which worked pretty nicely, but it still does a lot of atomic reference counting and weak references, and also a lot of heap allocation and pointer indirection. So it's not as fast as it could possibly be, I think. So there's probably still some room for improvement, and it's probably not useful yet for, say, use in embedded systems or something like that. And yeah, another issue is also that transactions are pretty dumb so far. So the way it's done is essentially there's a global lock on the entire graph of events whenever you want to do something. And after you're done, we release that. So there's not really any parallelism. Yeah, I've been thinking about ways to improve that, but so far, I've just tried to get at the correct semantics. Okay. Yeah, that's pretty much it. Thank you for your attention. And yeah, I take some questions now.
Hello. Yeah, you started out with an example where you put something into a sink and then assert that something comes out of the stream.
Mm-hmm.
But this implies that it's single-threaded. And you said it was thread safe. So are you always in a single thread, or can you give the stream to someone in another thread, and then you have timing issues, and you can't just assert like that?
It's so the way the send function works is actually synchronous. But it's thread safe. So if you were to, there's also an asynchronous variant of it. So you could put it in a thread and just send it through the system. The way it's done is thread safe. But in this example, if I had sent the event and asserted afterwards, I wouldn't have been sure that it had propagated through the system yet. So this is just why I made it synchronous in this case.
There is also implementation of RX Rust, so the reactive extension, which are used by Cycle. Did you look at that before writing Carboxyl?
I did look at that. I think it actually existed longer than my implementation. But what I found was that it was not, well, first of all, it was written at a time, I think, before Rust was really stable and it wasn't actively maintained. And looking at the implementation, it was really pretty complex. And so, yeah, I started from scratch basically because I didn't want to touch an existing code base that I didn't know what kind of problems there were in it. But I think it's not really usable at the moment, as far as I know.
Hi, so actually I have two questions. I didn't quite get what is the nature of streams right now. Is it pull-based or push-based? Because I saw the next functions. Okay.
The next function is really just a matter to satisfy Rust's iterator semantics. So essentially what happens if you attach an iterator to a stream, it just registers sort of a callback that puts something into a channel that has a queue. And if you have the iterator, you can just take from that queue. So that's just an intermediary mechanism to have something like a Rust iterator, but it doesn't really have to do anything with how the stream itself is implemented. Yeah.
Okay, and second is actually a thought. Because in React, some time ago, there was this thing called pure render mixin, where you could explicitly say that the component or function is pure. So wouldn't it be possible here to do the same thing?
So you mean to actually have the type system say, okay, this function is supposed to be pure, or?
So not necessarily the type system.
But
like
something.
in React, it was just a function or a mixin. So you could just say that this component is pure. So then the behavior would be different and optimized just for that.
Ah, okay, I see. I pretty much rely on the implementation on the fact that it is pure. If you would put something impure in there, it would break the semantics, and I don't know, things would happen that I couldn't predict. So all the functions should be pure. That being said, though, I mean, that can't be enforced by Rust because inherently it's still an imperative language. And while it has, so I can enforce immutability formally, it's still possible for you to, in a given function, to construct something that has inner mutability, such as a mutex, and just locally produce some temporary mutable state and access that. So it's not really possible to constrain that, but the implementation relies on it entirely. Yeah.
Okay, thanks.
I guess that would be it. Let's thank our speaker once again.